Today we will discuss the important concept from stereochemistry, that is the chirality. The Greek word che means the hand-like or handedness. If suppose that is our hand and second hand, okay, like that. From there you can see here the first hand, okay, that is thumb. The chiral object is can be defined as it must be non-superimposable and must not have any kind of symmetry. Okay, like that we can define the chirality. The molecule no having plane of symmetry and it is non-superimposable mirror images. These hands are non-superimposable to each other. Okay, suppose that hands looking like that and these hands are non-superimposable to each others. Therefore, these objects are the chiral objects. So the hands are the chiral objects. These are the conditions required for the chirality. No any plane of symmetry and it must be non-superimposable mirror images to each other. We have one example, that is lactic acid, and when you put the mirror images, when you put the mirror, you will obtain such kind of product, such kind of mirror image you obtain. Okay, OH and H. Okay, such kind of you obtain the mirror images. And this mirror image, the first mirror image is not superimposed on this mirror image. Okay, like that. These two molecules is like that. First molecule. Okay, you can see these two are the mirror images. Okay, these are the mirror. If you put the mirror, it shows the mirror images. Okay, these are the mirror images, but these are the non-superimposable mirror images. Okay, you can see at the red ball there is a blue one, and at the blue ball there is a red one. Okay, like that, these two molecules are not superimposable on each other. Like our hands are not superimposed to each other. The mirror images, these are the mirror images. Okay, these first and second mirror images, and these mirror images is not superimposable each other. This mirror image is not superimposed to you. Okay, these are mirror image, this mirror image. Okay, when you place the mirror, these are not superimposed to each other. Okay, therefore for chirality in molecule, there must be not plane of symmetry and these mirror images are non-superimposable to each other. These two conditions is required for the chirality. If a molecule is a chiral, then it rotates plane polarized light. Suppose an ordinary light is passes in all directions. Okay, alternate light, it passes in all directions. and when it passes through a nickel prism, it vibrates in only one direction. Okay, ordinary light vibrates in one direction only, and when you pass in nickel prism, it vibrates only a single direction. Okay, that single direction vibration of light is called as plane polarized light, and that is called as the polarizer. The nickel prism is called as the polarizer. Okay, that nickel prism is called. When ordinary light is vibrate in all directions, pass through the nickel prism, and it gives the plane polarized light. And when you put your compounds, okay, and when your plane polarized light it pass through this compound, it rotates. That plane polarized light, whether it is rotated to the left hand side or it is rotated to the right hand side. When it is rotated to the left hand side, it is a levo rotatory substance, and if rotates plane polarized to left hand side, it is a dextro rotatory. Okay, therefore by using the second nickel prism, you can find out at which angle your plane polarized light is rotated. Okay, therefore the chiral molecules rotates plane polarized light. Okay, there if molecule is the chiral, it definitely rotates your plane polarized light. When light is passed through, plane polarized light will pass through that solution of chiral molecule, it definitely rotates. Okay, this that is the optical active. Your chiral molecule should be optically active. Then Van Top, one of the scientists, is said that the carbon which is having 4 different groups is attached. Okay, such carbon. This carbon is having this artistic sign. You will give that carbon which is having 4 different groups is attached. That Van Top said that the carbon which is having 4 different groups is attached, that is responsible for the rotation of plane polarized light. And that carbon which is having 4 different groups is attached is called as asymmetric carbon. Okay, at the start the word is used was the asymmetric carbon, or that carbon is also called as the chiral carbon or chiral center. Most the word is instead of these today is used, the word is the stereogenic center or stereo center. Okay, these are the asymmetric carbons, chiral carbons, stereogenic centers or the stereo centers is nothing but that carbon which is having the 4 different groups is attached. And most correct word is the stereogenic center or the stereo center. The other way we can define the stereogenic center is by replacing or by interchanging. By interchanging 2 groups, we will obtain the new stereo center. We obtain the new stereoisomers by interchanging 2 groups. Any 2 groups, when you interchange, you will obtain the new stereoisomers. That is its enantiomer. You will obtain its enantiomer by you are interchanging these 2 groups or atoms. That is our stereogenic center. If you suppose that we have the lactic acid, and when you replaces at the hydrogen with OH, these 2 groups, when after interchanging, we will obtain the new its enantiomer. Okay, these 2 are the enantiomers. Okay, enantiomers is nothing but the non-superimposable mirror images. Okay, these are the mirror images, and when you put this molecule overlap with this molecule, you found there these 2 two molecules are non-superimposable to each other. Okay, therefore these two are the enantiomers to each other. We will discuss this concept enantiomer later after discussing all the concept of the chirality. The Van Top said that if the carbon has the four different groups attached, it shows the it is a chiral. It shows the chirality and it rotates the plane. It rotates the plane polarized light. But after the studying, it is found that though some compound has more than one chiral centers or stereo centers that may or may not shows the rotation of plane polarized light. We have the example of tartaric acid. The Louis Pasteur has studied this. When he studied this sodium salt of the tartaric acid, and he passed the plane polarized light through this sodium salt of tartaric acid, he found that there was no rotation of plane polarized light. Though this tartaric acid has two different stereo centers. Though it has two different stereo centers, it does not rotate plane polarized light. Therefore, it is considered as a chiral molecule. It's considered as a chiral molecule. When the two plane is passed through this compound, imaginary mirror plane is passed to this compound, or a plane passed through this compound, it divides that compound into two equal halves. Therefore, first center cancel the rotation by the second center. Okay, therefore the carbon which is having, or if in your molecule if there is a asymmetric carbon is present or the chiral carbon is present, it is not necessary it shows the chirality. If in your compound only one carbon is present and which is chiral one, it definitely show the chirality. But if more than one center, a stereo center is present, it maybe shows the chirality or may not show the chirality. It depends upon its structure or geometry. Remember, it depends upon its geometry, whether your molecule is the chiral or non-chiral molecule. Right? Okay, like that we will discuss which factors will decide the chirality in molecule. Now, Van Top said that for the chirality there should require the asymmetric carbon or the chiral carbon, but after the studying, it has found that though there is present the chiral centers more than one, it may show or it may not show the chirality. Okay, therefore the stereogenic center or the asymmetric center or chiral center will not decide the chirality of a molecule. Now, later study is said that the only stereogenic center or stereo center is not responsible for the chirality or not responsible for the optical activity. There are some molecule where there is a lack of asymmetric carbon or the chiral carbon. They shows the chirality. These molecules are, first is alkanes. Alkanes is there. Okay, in alkanes you can found there in alkanes does not have any stereo center, though it shows the chirality. Okay, therefore there is no necessity whether there is a chiral carbon is present or chiral carbon is not present. Okay, therefore stereo center not decides the chirality. Only stereo center, definitely stereo center define the chirality, but only stereo center is not responsible for the chirality. Because this is the alliance, and alliance is also shows the chirality. Then again one of the compound, okay, there is a geometric isomer also show the chirality, C double bond C. The biphenyl rings, okay, these are the another example of the, there is a biphenyl ring. This biphenyl ring is also the biphenyl ring is also show the chirality. Okay, this molecule, this is the planar one, and this is the like that. Okay, this like that. These are the planes. Okay, all the bromine and this. Okay, sorry, this iodine is there. Bromine and iodine. This is the this called the biphenyl compounds. And when this is the planar one, and this phenyl ring is the like that. Okay, like that. And here is the behind the this planes, behind this plane is the bromine, and towards yourself is the iodine is there. Okay, therefore this compound is also show the chirality. Okay, therefore we summarize these things. First things, if stereo center is present in molecule, only one stereo center is present, chiral carbon is present, only one, then it definitely show the chirality. But more than one stereo center is there, it may or may not show the chirality. It depends upon the geometry of a molecule. And third concept, we have seen that only stereo center will not decide the whether your molecule is the chiral or the non-chiral. Okay, these are the three important concepts we have seen. We have started with the stereo center, that chiral center, then more than one chiral center molecule, and then without the chiral carbon or without asymmetric carbon, your molecule may be chiral or the achiral. Okay, these two concepts. The very important one of the symmetry device is one of the device is useful for the to decide the molecule is the chiral or the non-chiral. Okay, let us discuss this, how the symmetry is useful for the chirality or achirality in a molecule. If molecule does not have plane of symmetry, inversion, or an alternative axis of symmetry, if the molecule lack of these three types of symmetry, then the molecule is definitely chiral molecule. Remember that. And if any of the symmetry is present within the molecule, then molecule is not chiral molecule. This is achiral molecule. Let us discuss the three symmetries. Okay, we are not including the axis of symmetry or identity. Axis of symmetry means what? When you rotate the molecule any angle, you will obtain the equivalent new arrangements of the that molecule. That is the axis of symmetry. And identity means any molecule you put as it is, or even molecule you rotate 360, nothing to do on the molecule. That is identity. These two will not included. We have not included in this discussion. But you have studied this 130 and 130 also. Let us start with the plane of symmetry. Plane of symmetry means an imaginary plane passes within the molecule which divides molecule into two equal halves. That is called as the plane of symmetry. We have an example, that is tartaric acid. This is an example of the tartaric acid. And when a plane passes through this tartaric acid which divides the molecule into two equal halves, therefore that plane is the plane of symmetry, and whether your molecule have the plane of symmetry, then this molecule is not optically active, or it's considered as a chiral molecule. Okay, therefore this molecule is, though it is having there are the two stereo centers, but due to the plane of symmetry it is not considered as a chiral molecules. We have another example, okay, like that Cis Dichloro Ethane. When you pass the plane, it divides that two molecule into two equal halves, same in this side and same in this side. It divides the molecule in two equal parts, therefore this is a plane of the symmetry. That molecule, it has the plane of symmetry and it is a chiral molecule, that is called as the chiral molecule. Number of example is there. If you rotate that molecule in 180 degree, and therefore it's again, when you rotate the molecule 180 degree, it's again give the equivalent structure. And 360, okay, the angle 360 upon 180 gives the 2, therefore axis of rotation is the C2, Cn is the C2, that is axis of rotation. When any angle you rotate the molecule, you will obtain the same or equivalent arrangements or equivalent molecule of the from its beginning molecule, and its after rotation obtain the equivalent molecule or equivalent, what you call it, equivalent in nature, therefore its C2 rotation is there. That is axis of symmetry. Now this is about the plane of symmetry, that is sigma, which is denoted by the sigma. Inversion is denoted by the I. If suppose we have the molecule, like that molecule is there, trans dichloroethane is there. At the center, when you pass through equal distance through the center, opposite direction, through the center you pass opposite direction, you will obtain the same atoms. So chlorine, same atoms. Through the center you obtain straight line. Okay, the straight line, you move the opposite to the straight line. Through that center, imaginary center, you obtain the same atoms or the groups. Okay, in this, when you move to this, you obtain the same chlorine. You move to this, same chlorine. You move opposite hydrogen. You may, okay, through this line you will obtain the same group. Okay, through this line you obtain the same group. Hydrogen. Through this line you obtain the same group. Through that spot you move the opposite in a two direction, then you will obtain the same atoms or group. That is nothing but the inversion, and it is denoted by the I. Okay, if you have the molecules like this, that is tartaric acid is there. Okay, CO, that is tartaric acid. Then okay, when at the center you move opposite direction to this, you will obtain COH. You obtain to that direction, you will obtain OH. You will obtain through the center hydrogen. Okay. Therefore, that molecule also show the center of symmetry, and center of symmetry means molecule is optically inactive and molecule is achiral, not a chiral molecule. Okay. This molecule is also a chiral molecule. This molecule is also a chiral molecule. Okay. Therefore, if plane is present, inversion is present, alternating axis of symmetry is present, then molecule is the chiral molecule. All these things is absent, then and then your molecule should be chiral molecule. The third thing is an alternate axis of symmetry. Alternate axis of symmetry means what? Firstly, you have to rotate molecule by any angle and pass the plane perpendicular to that axis you have rotated previously. Okay, if you rotate that molecule that axis, then plane is passed perpendicular to that axis. Plane is passed, you rotate molecule, plane firstly you rotate and then plane is passed which is perpendicular to this axis. Okay, this is denoted by Sn. Okay, S is the N is the axis. Okay, number of axes. Okay, how which angle you move, that is the N is the angle. Okay, if you move the 360, then if you move the angle with the 180, therefore 180 360 upon 182, therefore N is equal to 2. If you rotated the molecule in 90 degree, then it is 360 upon 94, then your axis is the C2 or C2 axis. Okay, C4 axis. Okay, like that. N is denoted by the rotation. Okay, N is the rotation of the axis, about which axis your molecule is rotated. In alternating axis of symmetry, we will take the example. By using that example, you can get the idea what is meaning of alternating axis of symmetry. 1, 2, 1 and 2. Firstly, you rotate that molecule through 180 degree Celsius. 180 degree. You rotate that molecule 180 degree. Then after rotation, you found there S2 will move there, S2, then Cl1, then Cl2 and H1. Okay, after 180 degree rotation, you will obtain this. Okay, firstly you rotate like that and you pass the plane through perpendicular to this. Okay, this axis, you pass the plane perpendicular to this axis. Then this plane, after the passing the plane, your hydrogens will come here. They're interchanging through this plane takes place. Okay, therefore after passing the plane, you will obtain Cl2 is there, S2 is there, then Cl1 and S2 will move to there. First orientation and you will obtain the equivalent orientation. This is the equivalent orientation you obtain from the first. Then this is the your SN axis. This is called as SN axis. 180 is the you rotated 180, then 360 upon 180 is equal to 2. Therefore, it is the S2 axis. This is called as the S2 axis. This is all about the an alternating axis of symmetry. We rotates the molecule through an angle and then pass the plane perpendicular to this rotated axis. Okay, after rotation you will not may or may not obtain the same orientation. This orientation is the different. This is not equivalent. First and second is the equivalent. Not same, it is equivalent. Same means what? Its identity. Okay, here is a Cl2, Cl1. Okay, that is not identity. Equivalent orientation is obtained. First and third is the equivalent orientation. After firstly you rotated molecule, then pass the plane perpendicular to that axis, you will obtain the same orientation. Okay, this is about the alternating axis of symmetry. Then there is a concept, that is sigma is equal to S1 and inversion is equal to S2. For this we have an example for S1 sigma. If you have the example like that, same example we have taken here, same trans molecule we have taken 1 and 2, 1 and 2. When you rotate, okay, if suppose you rotated that molecule through 360 rotation, okay, if you rotate through this 360 rotation, no, you will not obtain the S2 axis. If you rotate through the like that rotation, okay, your axis is passed through like that and you rotate the 360 rotation. After you obtain the 360 rotation, Cl1, okay, as it is, 360 rotation means as it is. Okay, you will obtain the as it is molecule. And then you pass the plane this one, you pass the plane like that, okay, because an alternating axis of symmetry means the you firstly rotate the molecule and pass the plane perpendicular to this plane is the perpendicular to your molecule is rotated like that, and this is the plane perpendicular to this axis. Okay, we already discussed in symmetry. Okay, therefore you pass the plane, you will obtain the such kind of molecule which is the equivalent with the first one, which is equivalent for the first one. If suppose you rotate 360, you pass the plane through this molecule, you pass the plane, you will obtain is the such type of the molecule H2, H1 and Cl2. After passing plane and after doing this, okay, firstly you rotate the 360-degree rotation and then you pass the plane, you will obtain this molecule. And when you only pass the plane, okay, there is sigma, okay, the plane is passed, that plane you pass the plane through the planar, that molecule is the planar, okay, that molecule is loose like that, that is a planar one, molecule is planar, you pass this plane, okay, the planar, you pass the plane. If that page is the planar one, therefore you pass through that such a page, that molecule is the planar, therefore you pass the plane through all these items. Okay, therefore sigma and this total operation is firstly rotate and you then you rotation 360 means as it is molecule, you put the as it is and then you pass the plane. For this orientation of the molecule and this orientation of the molecule, these two orientation is same orientation, therefore this is sigma, hence proved that sigma is equal to S1 axis. 360 is there, therefore 660 upon 360 is equal to 1. Your rotation is the S1, therefore sigma is nothing but the S1 axis. Okay, for the second assumption is I is equal to S2. For this we have an example is there. This example, trans 1,2-dichloro ethane. Firstly, okay, you have to perform the S2. Okay, you have to firstly perform the S2. S2 means what? 2 means the 360 upon 2. You have to rotate the molecule 180 degree. If you rotate first 180 degree rotation, okay, through this you rotate this molecule, you will obtain the such kind of orientation which is not equivalent of the first orientation one. Okay, you rotated the molecule, then you pass the you rotate that molecule through this, therefore you have to pass the perpendicular. Okay, your molecule is rotated like that, therefore you have to pass the plane perpendicular to this axis. Okay, that is the your SN. Okay, total operation is the S2 operation. Okay, therefore you pass the plane, you will obtain Cl2, H is reflect in the plane in this direction, H1 is reflect to this side, Cl2 is reflect on this side in this plane. Okay, therefore you will obtain such orientation. Okay, this and this orientation is the equivalent orientation. Equivalent means not same, equivalent is the different orientation but equivalent to this molecule. Okay, this is S2 operation, then you perform the I operation, inversion. Inversion means through the center you move the straight line, you will obtain the same atom. Through the center you move the straight line, you will obtain the same atom. Okay, and you will invert the molecule, the atoms. Okay, therefore you invert, Cl1 will be at this point, Cl2 will move toward this. Okay, after the doing the operation, inversion operation, H2 and H2. Okay, you will obtain this orientation and the this orientation is the same orientation. Okay, after doing S2 operation and after doing inversion, it is same one. Therefore I is equal to S2. I is equal to is nothing but the S2. Okay, I is nothing but the S2. There are therefore by using only alternating axis of symmetry you can predict the whether your molecule is the chiral or non-chiral, because these are the such you remember all these things, plane of symmetry, not necessary. Okay, by using only alternating axis of symmetry, you can define the chirality in a molecule, whether a molecule is chiral or non-chiral. And in this molecule, because your plane is nothing but S1, your inversion is nothing but the S2, because these are the 3 points. By using this, you can predict the chirality of molecule. If plane is nothing but the S1, inversion is nothing but the S1, okay, all these things becomes equal to this. Okay, therefore, only by using an alternating axis of symmetry, you can predict the chirality in a molecule. Okay, therefore, if SN axis is present in a molecule, that molecule is a chiral molecule. If SN axis is present in a molecule, not present in molecule, therefore that molecule is a chiral molecule. Okay, therefore, if molecule is there and there is a SN axis present, then molecule is the achiral molecule. If SN axis is absent, then molecule is the chiral and dissymmetry. Chiral or other you can call it as the dissymmetry. Same word, chiral and dissymmetry. And if CN axis is absent, then molecule is the asymmetric. It is called as the asymmetric. Okay, this is the conclusion we have driven from this long discussion only. And by using an alternating axis of symmetry, you can predict chirality in a molecule. If SN axis of symmetry is the present, then your molecule is a chiral molecule. Therefore, by using only alternating axis of symmetry, you can predict chirality in a molecule. This is all about the chirality, very important concept. That is all about the chirality. Thank you very much.